Assalamu alaikum wa rahmatullah. Welcome back. This is Dr. Muhammad Saad, and we are continuing our lectures in computer communications and networks. Specifically, we would like to continue our discussion in the transport layer, and perhaps the last thing that we have talked about is flow control. And we had one important example that we called the window management example. Let's just have a peek. So this is something that we covered last time. We talked about window management, which is a way to achieve flow control, or this is the way for TCP to do flow control. How does this happen? It happens as follows, just as a reminder so that we can continue. This is the TCP header. We talked about the TCP header in full detail. One of the fields is called window size. Now that window size allows the receiver, the receiving host of the TCP connection, is allowed to specify or announce the amount of data that the sender is allowed to send before stopping and waiting for the acknowledgement. So the receiver specifies a window size with every acknowledgement, and then the sender sticks to this window size so that we avoid the sender from overwhelming the receiver if it's too slow or if its buffer is full. So this is something that we talked about here in full detail, so please refer to the previous lecture. This is how TCP does flow control. Now what about admission control? To introduce this topic, this is a nice basically analogy here. So imagine the following. This is our source that sends the data, and this is our final destination, and in between we have the network. Now here we have the following problem. The receiver has a small capacity buffer, so the receiver has a small capacity, it is slow. So that's why the sender may want to slow down to avoid overwhelming this receiver. Although the network is wide open, it has a large capacity. However, the sender needs to slow down to avoid overwhelming a slow or small capacity receiver, and this is what we call flow control. So what you see here is basically flow control, which is done using that window size, which is specified by the receiver in every acknowledgement. By the way, that window size is also called the receiver window or the advertised window. Now, in networking, we also have another problem that might occur in addition to the receiver. Basically, we could have the following situation, which is here on the right hand side. So we have a large capacity receiver. So our receiver, our receiving host, has a large capacity buffer. It is fast. It can receive all the data basically that the sender is sending at a fast rate. However, the sender may want to slow down to avoid overwhelming the network itself. So as you see, the network between sender and receiver might be congested, so it cannot handle that fast transmission. That's why the sender may want to slow down. So what you see on the right here, this is what we call congestion control. So flow control, slowing down for the receiver, congestion control, slowing down for the network. So this is basically what it is. Now we understand already how TCP or the transmission control protocol handles flow control. To handle flow control, we have something called the receiver window, which is basically specified in every acknowledgement. So the receiver specifies this value by itself. The receiver announces a window size in every acknowledgement, and this is what we call the receiver window, and the sender needs to stick to this value. However, we still have the problem of congestion. So we have also the problem of congestion. So how do we deal with that? When do we decide to slow down to take care of both? Take care of the receiver and take care also of the network congestion. So the way this is done basically is that the internet realizes that both problems exist. We have the network capacity or congestion problem, and we have also the receiver capacity problem. We understand very well that receiver window, which gets announced in every acknowledgement. For now, let's assume that the sender knows something called a congestion window. So we have the receiver window, and we also have the congestion window. Now what is the receiver window again? It is the number of bytes the sender is allowed to send before stopping and waiting for the acknowledgement so that we don't overwhelm the receiver. Okay, what is the congestion window then? It is again the number of bytes. It's also a window specified in bytes. The congestion window is the number of bytes that the sender is allowed to send before stopping and waiting for the acknowledgement. However, This is done for the sake of preserving the network, for the sake of avoiding network congestion. So we have two windows, the receiver window and the congestion window, assuming that the sender knows both values. So I know how much the receiver can handle and how much the network can handle. If I choose the smaller of the two, this will make sure that I'm being careful towards both the receiver and the network. Here we have an example that illustrates this idea. Imagine that the receiver announces an 8 kilobyte receiver window. So the receiver says you can send up to 8 kilobytes. I would be okay with that. However, somehow, and until now, somehow, exactly how we will understand later, somehow the sender knows also that 4 kilobytes, if I send more than 4 kilobytes, I will congest the network. So the receiver says send 8, but the network cannot handle more than 4. So we have 8 and 4. The smaller of the two is the 4. So that's why I can send at most 4 kilobytes. In this example, imagine another motivating example. Imagine the receiver says you can send 8. So the receiver window is equal to 8 kilobytes. However, I know that the network can handle up to 32 kilobytes without congestion. So I have 8 and 32. What is the smaller of the two? It is the 8. So finally, I will send only 8 kilobytes. Eventually, I will send my sender window will be the smaller of the two, which is the 8 kilobytes. So let's put things together. So we have a receiver window. Imagine I'm the sender. As a sender, I will need to know what is the receiver window. How will I know about it? I will check this value from the acknowledgement. With every acknowledgement, I just check the window size which is specified. I have the receiver window. As a sender, I just need to look it up. Now the congestion window is something else, and you will understand in the next slides that this is something I have to calculate. As a sender, I need to calculate this value myself given my perception or my understanding about the network congestion, and we will talk about it today. Tamam? So the receiver window, I just look it up from the acknowledgement and it gets announced by the receiver. The congestion window is a value in bytes that I calculate myself. Once I have both, I choose the smaller of the two, and this is what we call the sender window, and this is at the end of the day what I should send. So this is the idea of congestion control together with flow control. Flow control is done completely, we understand it completely through the window management example. We understand that the receiver announces a dynamically changing window size and the sender just needs to look it up from the acknowledgement and then stick to it. Now what about congestion control? How do we calculate the value of the congestion window, this congestion window? How do we calculate this value? And this is what we mean by congestion control mechanisms or congestion control algorithms. Now in the following slides, I would like to tell you how the TCP protocol, the transmission control protocol, deals with congestion. How does it do congestion control? So the main idea is as follows. Before we continue, we just have a definition here. So for any established TCP connection, we understand from last time that TCP is a connection-oriented protocol. So before I start sending you data, the sending host needs to get in agreement with the receiving host to establish a connection. And it is done by three-way handshake, by sending a request, receiving an acknowledgement, and then I send another acknowledgement. So after these three steps, we have an established connection. We have an established TCP connection between a sending host and the receiving host. Once we have this established TCP connection, the sending host can start sending data segments and the receiving host will start sending acknowledgement segments. Now, we have one parameter which is fixed for the TCP connection. It is called the one maximum segment size, one MSS in short. What is this one maximum segment size? That one maximum segment size specifies in bytes the maximum amount of data that the sender can send in form of one segment. Not in total, because in total it would be the window size. No, the one maximum segment size is just a fixed parameter for a TCP connection which specifies how much data in bytes the sender is allowed to send as one segment. So let me give you an example. Imagine the one maximum segment size is equal to 1024 bytes or 1 kilobytes. What does that mean? It means that at any time the size of any segment cannot be more than one maximum segment, which is 1 kilobyte. Any segment that comes from the transmitter cannot be more than 1024 bytes or 1 kilobytes. This is the role of the one maximum segment size. Okay, imagine given this one maximum segment, which is 1K, 1 kilobytes. Imagine that the sender is allowed to send 3 kilobytes in total. So given the values of these receiver window and congestion, and even using the top example here, imagine that the receiver window is equal to 8K and the congestion window is equal to 4K, which means that the sender window is equal to 4K. So according to these numbers, the sender is allowed to send 4 kilobytes in total. How does the sender send 4 kilobytes in total if the one maximum segment parameter is only 1 kilobyte? It means that the sender can send 4K, however, in form of 4 different segments. So this is the role of the one maximum segment. It just specifies the upper limit on one segment. However, if the total window size is more than that, it means that I can send more. However, it has to be multiple segments and not just one. I can send multiple segments, and by the way, the receiver can acknowledge multiple segments at the same time, because the acknowledgement number is just the byte that I'm expecting next. So this is the role of the one maximum segment. Now, how does TCP congestion control work? TCP congestion control, again, is about how the sender maintains the value of the congestion window. The rule is very simple. The congestion window at the beginning of the TCP connection is set to the value of one maximum segment. So that's the initial congestion window value. So the congestion window at transmission number 1 at the beginning of the connection is equal to one maximum segment. So in case one maximum segment is 1 kilobyte, it means that the congestion window at the beginning of the connection is set to one maximum segment, which is equal to 1 kilobyte. And then I send my segment. The deal is as follows. If the sender thinks that there is congestion, with the next transmission, the congestion window value, with the next transmission, the congestion window value needs to be decreased. However, if the sender thinks that there is no congestion, the congestion window value needs to increase. With the next transmission, the congestion window value will increase. So this is the deal. Initially, at the first transmission over the connection, the congestion window is equal to one maximum segment, that parameter, which is one maximum segment, the basic segment size. And then we send our segment. If we think that there is no congestion, the congestion window will increase, it will go up. If we think that there is congestion, the congestion window will go down. Go up by how much and go down by how much, this depends on the actual mechanism that we deal with. We have several TCP congestion control mechanisms, and in this lecture I will focus only about TCP Tahoe, which is a well-known TCP congestion control mechanism, and it is very close to what the internet is implementing nowadays, TCP Tahoe. So this is what we will focus on. But before we go to the details of TCP Tahoe, I just want to make a comment here. So let me remind you quickly, what is the idea of any TCP congestion control mechanism? The initial congestion window is equal to one maximum segment size. If this segment is, if we send the segment and then we perceive or we think that there is no congestion, with the next transmission the congestion window will increase. However, if we think that there is congestion, with the next transmission the congestion window here that we have been talking about, the congestion window, will decrease. Now, the only remaining question, which is also written here, the only remaining question, how does the sender recognize congestion? If I'm sending my first segment, how do I recognize that there is congestion? And how TCP does this is basically by packet losses. So by segment losses or by packet losses. So let me put everything together. My initial congestion window is one maximum segment, assuming this is 1 kilobytes. So I build a segment which cannot be more than 1 kilobyte. I send it, and then I wait for the acknowledgement. If I get the acknowledgement before timeout, if I successfully get the acknowledgement before timeout, as a sender I will assume that there is no congestion. Because if I get the acknowledgement, it means that my segment went through successfully. I received the acknowledgement also successfully, which means that the buffers were not full and nothing got lost. So if I get the acknowledgement before timeout, I will assume that there is no congestion, and with the next transmission I will increase the value of the congestion window. So with the next transmission I will send more data. Now, if I send that first segment, which has a size of one maximum segment, and I don't get the acknowledgement, if I don't get the acknowledgement, what does that mean? It means that something got lost along the way. Something got lost, and this is the reason for packet losses or segment losses is usually congestion. When we have congestion, it means the buffers in the core of the network, some of them are full. So when my packet tries to cross this buffer to go over the next link, it will get lost. So eventually my segment or my packet will not arrive, and the receiver will not send an acknowledgement. Again, the sender detects congestion by packet losses, by segment losses. It's the same thing. And in short, it is when a timeout occurs. If the sender times out before receiving the acknowledgement, then we would say that we have congestion. Does this mean congestion for sure? So if the sender times out, if I send a segment and I don't get the acknowledgement, does this mean that this is congestion for sure? No, it is only an assumption, and it's basically a good assumption in wired networks. In wired networks like today's fiber optic internet, the internet that has fiber optic links or copper wire links, for these kinds of wired networks, the main reason for losses, for packet losses, is congestion, is basically when the buffers get full. However, if you have a wireless network, then maybe packets would get lost because of other reasons, not only congestion but also interference and noise and the channel condition and so on. So basically in these kinds of wireless networks, if we get a packet loss, if I time out without getting the acknowledgement back, it does not necessarily mean that there is congestion. So all these mechanisms that I'm talking about here, TCP congestion control, are suitable for wired networks. So this is the question which is here. Basically, I just tried to answer it. So this assumption that congestion is detected by packet or segment losses, this assumption is basically good for today's wired networks. Why is this true? Because the main reason for packet losses in a wired network is congestion. So if we get a packet loss, we can assume that there is congestion, and this is most likely correct. This is a good assumption. However, if you have a wireless network, we cannot really assume that there is congestion just by seeing a packet loss. That's why in wireless we have to deal with some other mechanisms. So in short, as I mentioned twice, in short, the TCP congestion control mechanism that we will talk about is more suitable for wired than wireless networks. Now, how does it work in full detail? We would like to focus on TCP Tahoe. Again, as I mentioned before, it is very close to what happens over the internet nowadays. So how does TCP Tahoe work? Let me now skip these slides and go directly to TCP Tahoe. The main idea, again, before the main purpose of TCP Tahoe is to come up with a mechanism for the sender to calculate the value of the congestion window. To calculate the value of the congestion window and update this value with every transmission. The sender needs the value of the congestion window so that it can decide how much data it's allowed to send with every transmission. How does it calculate this congestion window value? As in the general setup, we mentioned here that in general, any TCP congestion control mechanism initializes the congestion window to one maximum segment size first, and then it will start increasing or decreasing that value depending on whether it has congestion or not. So TCP Tahoe is not different from that. At the very beginning, the congestion window is equal to one maximum segment size. But in addition to the congestion window, TCP Tahoe has another parameter. We say third, we mean in addition to the congestion window and the sender window, we have these two parameters, the congestion window for congestion control and the receiver window for flow control. In addition to these, in TCP Tahoe we have also a threshold. Usually the threshold starts with 64 kilobytes. Now, what is the role of this threshold? Now, to explain how TCP Tahoe works, we have the explanation here, but I prefer to explain it on my illustration here. So we have the threshold. So this is our threshold value. That threshold is measured in the same units as the window size in bytes or in kilobytes. Now we're talking about TCP Tahoe. As usual, as in any TCP congestion control mechanism, we have a congestion window. So CW, let's think of this as the congestion window. And this is the value of the congestion window at the very first transmission over this TCP connection. So we have a newly established TCP connection. We send the request, can I establish, you acknowledge, and so on. So we have a new TCP connection and we start sending segments. Before I send a segment, let's set the congestion window first. And initially in TCP Tahoe, the congestion window is set to 1 maximum segment size, the equivalent in bytes of 1 maximum segment size. If the 1 maximum segment is 1 kilobyte, then the initial congestion window is also 1 kilobyte. This is the first congestion window. What do I do next? Assuming that this will be the bottleneck, so assuming that the congestion window will always be less than the receiver window, it means that this is the value that we will send. So that 1 maximum segment size, or the equivalent in bytes of 1 maximum segment size, this is what I'm allowed to send. So I put this amount, the 1 maximum segment, like 1 kilobytes or so, I put it in a segment and then I send it. If I receive the acknowledgement without timeout, it means I can increase the congestion window. I will increase the congestion window by doubling its value. So the next congestion window at time 2, at transmission number 2, becomes double that of the congestion window at time 1 by multiplying by 2. So basically we multiply by 2 and then the next one we multiply by 2. So the first congestion window was 1 maximum segment. The next one becomes 2 maximum segments, the next one becomes 4 maximum segments, and so on. We keep doubling as long as we don't have timeouts, as long as our transmissions are successful, and also as long as the congestion window did not reach the threshold yet. So you can think of the x-axis here as time, and the y-axis as the value of the congestion window, and we are dealing with what is the value of the congestion window at the different times. Again, the initial congestion window at transmission number 1 was the equivalent of 1 maximum segment. If 1 maximum segment is 1 kilobyte, then the first congestion window is 1 kilobyte. Again, let me repeat, what do we do now? We send a segment that has only 1 kilobyte, we send it to the receiver. If the final receiver receives it and sends me the acknowledgement and I get the acknowledgement in due time before timing out, it means that I will understand that there is no congestion, right? If I get the acknowledgement without timing out, it means that there is no congestion. So I will double the congestion window, I make it 2 kilobytes. Now I'm sending 2 segments. Each one of them is 1K because that's the value of the 1 maximum segment. So I'm sending 2 segments. In total, I'm sending 2 kilobytes. If the receiver sends me the acknowledgement and I get them before timing out, it means still that there is no congestion and I can double the congestion window. The next one becomes 4K. The next one becomes 8, the next one becomes 16, 32, and so on. So we have an exponential increase because we keep doubling the congestion window. How long does this doubling last? Until the value of the congestion window reaches the threshold. So imagine that, of course, let me just tell you now, this is just an overview. However, we will have a detailed numeric example that I will keep talking about after I finish the overview. Again, let's assume that the threshold is 64 kilobytes. The threshold is 64 kilobytes. The first congestion window is 1 kilobyte because we assume that 1 maximum segment is 1. And then if I send the segment, I get the acknowledgement without timing out, the next congestion window becomes 2 kilobytes. So I will send 2 kilobytes in form of 2 segments. If they are successful and I get the acknowledgements without timing out, the next congestion window becomes 4, and then 8, and then 16, and then 32, and then 64 kilobytes. Now when the congestion window is 64 kilobytes, what does that mean? It means that I'm allowed to send 64 kilobytes. I'm allowed to send 64 kilobytes, of course in form of 64 segments, because in this example we assume that the 1 maximum segment basically is the equivalent of 1 kilobyte. So when the congestion window is equal to 64K, it means I can send 64K, but these 64K have to be 64 separate segments. I send them all. At that time I send them all, and I'm waiting for 64 acknowledgements that acknowledge these segments. If I get them all, if I get all these acknowledgements without timing out, it means that there is still no congestion. So I should be increasing the congestion window. However, once I reach the threshold, I will increase the congestion window as long as I don't have a timeout. However, I'll be more careful. I will increase by adding only one maximum segment. So here we have an exponential increase because with every transmission we double the congestion window. If I reach the threshold and I'm still okay, I still think that there is no congestion because we don't have timeouts, I will keep increasing the congestion window by adding one maximum segment. In our example, one maximum segment was 1 kilobyte and the congestion window reached 64K. With the next transmission, the congestion window will become 65 and then 66 and then 67 and so on. Imagine we keep increasing without any timeouts until the congestion window becomes 70 kilobytes. Let's say it becomes 70 kilo. At that transmission, the congestion window is equal to 70K. What am I doing now? I'm still stopping here to slow down. What do I do now? I have to send 70 different segments. Each one of them contains 1K because the one maximum segment is 1K. So at that transmission, I'm sending 70 segments. Each one of them is 1 kilobyte. So in total, I'm sending 70 kilobytes. What will I wait for? I will wait for 70 acknowledgements. If I get all 70 acknowledgements without timing out, it means I will still increase the congestion window. However, in this example, in this illustration here, I assume that at that time, we get a timeout. So here, when the congestion window was equal to 70, I'm sending 70 segments and I'm not receiving all acknowledgements. I will get one or more timeouts. I will know that something got lost. In the transmission, something got lost. What will that indicate? It will indicate that there is congestion. Now, what should I do? If there is congestion, I should decrease the congestion window. You know, when I was increasing in the increase phase, I was multiplying by 2 until the threshold, and then I will adding one maximum segment, not one as 1 byte or 1 kilobyte necessarily. I'm adding one maximum segment. So if in another example, the one maximum segment is equal to 2K, it means in each step here, I'm adding 2K, 2K, and so on. So I reach 70 and then I get a timeout. What should I do? I should decrease the congestion window. In TCP Tahoe, when a timeout occurs, two things will happen. Remember, two things will happen. First of all, the next congestion window goes down all the way to one maximum segment again. So although we reached 70 kilobytes as the congestion window, the next congestion window after the timeout will be 1 kilobyte. And guess what? We will be applying that doubling again. So this doubling, this exponential increase, 1 and then 2 and then 4 and then 16 until the threshold, this will be applied again. So this is the idea of how things work. At the same time, so this is the first thing that happens. When a timeout occurs, the next congestion window becomes one maximum segment. And the threshold will also change. The threshold will become half of the current congestion window. In our illustration here, we assumed that the congestion window reached 70 kilobytes. So the new threshold will become 35 kilobytes, which is half of the previous congestion window. Now we will just go on. The congestion window at that time is equal to 1, which means I'm sending only one segment that has 1 kilobyte. If it's successful, if there is no congestion because I get the acknowledgement, I will double it. It becomes 2, it becomes 4, it becomes 8, it becomes 16, and so on until I reach the threshold. After the threshold, I will continue my linear increase again. Let me just mention to you something as a definition here. That phase in which we are doubling the congestion window. In other words, as long as the congestion window is still below the threshold and we don't have any timeouts, it means we double the congestion window. That phase here of the doubling is called slow start. So this phase is called the slow start phase of TCP Tahoe. Why do we call it slow start? It might look like a contradiction because we are doubling. So when we double, it means the increase is faster than when we add 1. However, it is still called slow start. And the best way to understand why we call it slow start is if you look here at this phase instead of looking at the beginning. When did we get the congestion window equal to 1? When a timeout occurred. We had reached 70 already. We had reached 70 kilobytes as a congestion window, and at the same time we got a timeout. So we wanted to reduce the congestion window. Since we reduced it all the way to 1, So we did not cut it by half or anything like that. We did not reduce it by 1. No, we went all the way down to 1. That's why we call it slow start. We start slow. We will, after timeout, we will start with a very low congestion window. However, we will speed up the increment until we hit the threshold. And this is the philosophy of TCP Tahoe. Basically, senders, they don't know exactly how much the network can handle without congestion. They don't know because the network is inside, it's in the core. We have routers and we have links that we don't have access to and that we don't know. So the reason is, basically the idea is as follows. Given that, the idea is as follows. Since I don't know how much the network can handle, I start with a small congestion window. So I send this amount, waiting for the acknowledgement. If it's successful without timeout, I will increase by doubling. If I'm fine, I will double again, and so on until I reach the threshold. If things are still fine and I still don't have a timeout, I want to increase the congestion window, but after the threshold, I'm just being more careful. That's why I'm adding only 1 segment with every transmission. This is the main idea of TCP Tahoe. I think the best thing to do is to look at this example, and it will explain in full detail with numbers what's going on. So again, on the x-axis, we have the transmission numbers. So first transmission 0, transmission 1, transmission 2, 3, 4, and so on. Transmissions that we're just counting, we're giving them indices over a TCP connection. Okay? By the way, if this is the first transmission and this is the second, so transmission 0 and transmission 1, what is the time between them? So if this axis is time in seconds, what is this time between the first transmission and the second transmission? You know, in TCP, if I'm sending you a segment and then I finish all my data, I have to wait, or I finish all what I'm allowed to send as in the window size. If I send you my data in form of segments, I have to stop and wait for the acknowledgement. Now, the time to send my segment plus the time to receive your acknowledgement is called the round trip time. After a round trip time, I can send something new. So basically, the time in seconds or milliseconds between transmission 0 and transmission 1 is the round trip time. The time between transmission 1 and transmission 2 is the round trip time, and so on. But for simplicity, for every transmission as an index, transmission 0, 1, 2, 3, and so on, we need to decide what is the value of the congestion window. So on the y-axis, we specify the value of the congestion window in kilobytes, assuming that we are talking about TCP Tahoe, Now here, in this example, we have a threshold here, and the threshold is equal to 32 kilobytes. It's just given to us. The threshold is 32 kilobytes. Now, the first congestion window is equal to 1. So this value here on the y-axis, that's 1 kilobyte. Why? Because in this example, put a note on the side. In this example, the one maximum segment size, this one maximum segment parameter here, the one maximum segment parameter has a value of 1 kilobyte. I will make a comment at the end, how will things change if this maximum segment size has a different value, 2 or 3. And then when we meet each other in a live session, I will also show you a more general example that I want you to be able to deal with, inshallah. So at the very beginning, at the first transmission number 0, the congestion window is equal to 1 kilobyte. What do I do then? I send my segment that has only 1K. I wait for the acknowledgement. If I get it without timing out, does this mean congestion or no congestion? It means no congestion because we don't have a timeout. Should I be increasing the congestion window or decreasing the congestion? I should be increasing the congestion window by doubling, because CW has a value of 1, which is much less than the threshold 32. So I will double. So the next congestion window becomes 2 kilobytes. Now when the congestion window is equal to 2 kilobytes, what do I do next at that transmission number 1? It means I can send 2 kilobytes, right? I send them by sending 2 separate segments, because in this example again, we assume that 1 MSS is equal to 1K. So when the congestion window is equal to 2, I'm sending 2 segments, waiting for 2 acknowledgements. If I receive them, it means that there is no congestion and I can still double. So the next congestion window at transmission 2 becomes 4. If I'm still fine, no timeout, I'm sending all 4 segments, getting all 4 acts, it means that I can double. So at transmission 3, the congestion window becomes 8. If I'm fine, no timeout, it becomes 16, and then it becomes 32. So this is the slow start phase, in which the congestion window doubles with every transmission, assuming that we did not see any timeouts here. So with every transmission, I'm getting all the acknowledgements. So here, when the congestion window is equal to 16, I'm sending 16 segments, waiting for 16 acknowledgements. I get them all without timing out. I get them in due time before timeout. It means I'm still successful. I will assume the network is not congested, and I will double the congestion window. I make it 32. Now what happens when the congestion window is equal to 32? It means I'm sending 32 segments, waiting for 32 acknowledgements. Imagine that I'm getting all acts without timing out. Does this mean congestion or no congestion? Still no congestion. Should we increase or decrease the congestion window? We should increase the congestion window. However, since I reached the threshold, I will increase by adding only 1 maximum segment. So here at transmission 6, the new congestion window is equal to the old one plus 1 maximum segment. So it's equal to 32 plus 1 kilobyte, because the 1 maximum segment is 1 kilobyte. So it becomes 33. Now let's speed up the description here. 33 kilobytes. And then assuming no timeout, it becomes 34, 35, 36, 37, 38, 39, 40 kilobytes. So at transmission 13 here, at transmission 13, my congestion window is equal to 40 kilobytes. Let me slow down the description again. What happens at that time? It means at that time, at transmission 13, I'm sending 40 kilobytes as 40 segments. I'm sending 40 segments. Each one of them is 1K. Again, because 1 MSS is equal to 1K. So I'm sending 40 segments, waiting for 40 acknowledgements. If I get them all, I would increase again. However, in this example, I'm assuming that here at that transmission, I'm getting a timeout. At least one of these 40 acknowledgements is not arriving in time. So I get a timeout. If I get a timeout, what does this mean? It means that something got lost in the network. If something gets lost, what do we assume? We assume that there is congestion. If there is congestion, what should we do with the congestion window? I explained to you from the beginning that we should decrease the congestion window. According to TCP Tahoe, we decrease by going all the way down to 1. We go all the way down to 1 maximum segment. So although at transmission 13 CW is equal to 40, in other words, CW index 40 is equal to 40 kilobytes. I mean CW index 13, sorry. CW index 13 is equal to 40 kilobytes, but we get a timeout. So CW index 14, did I say 14 here? Again, CW index 13 is equal to 40 kilobytes, but we get a timeout. So CW index 14 is equal to 1 kilobyte only, because that's the 1 maximum segment. So this is the first thing that happens when we get a timeout. When we get a timeout, the next CW becomes 1 maximum segment, which is 1 kilobyte in this example, because in this example, we assume that 1 maximum segment equals to 1 kilobyte. What else happens? This is the first thing that happens after a timeout. The second thing, we have to update the threshold. The threshold becomes different, and it becomes half. A famous mistake is to say half of the previous threshold. No, it is half of the previous congestion window. What was the current congestion window? The last congestion window reached, it was 40. 40 divided by 2 is 20. So that 20 kilobytes, this is the new threshold. Let's continue transmission by transmission and follow the values of the congestion window. Now at time 14, CW is equal to 1 again. I send a segment. If I get the acknowledgement, I will double the congestion window. It becomes 2. Doubling again becomes 4, assuming that here we don't have any timeouts. So 1 and then 2. Doubled, it becomes 4. Doubled, it becomes 8. Doubled, it becomes 16. And then we have a special case. Focus with me. Focus with me now. We have something very important here. It's a very important special case. When we doubled the congestion window from 8, it became 16. Now at that time, which is transmission number 18, at transmission number 18, I'm sending 16 segments, waiting for 16 acknowledgements. I get them all without any timeout. It means I should increase. Should I increase by doubling or by adding 1 segment? by doubling because I'm still below the threshold. So if I double here 16, it becomes 32. However, the threshold is 20. I don't go beyond the threshold at once. No, if my doubling wants to go above the threshold, it means that with the next transmission I just go to the threshold. So we have to snap to this threshold. So again, when a timeout occurred, the congestion window was 1, a maximum segment, which is equal to 1 kilobytes. 1 and then 2 because we double, and then 4 because we double, and then 8 and then 16 because we double, and then it wanted to be 32, but that's not allowed, so we have to go to 20. So the next transmission number 19, the congestion window is equal to 20 kilobytes, which means at that time I'm sending 20 segments, waiting for 20 acknowledgements. Okay, if I'm sending 20 segments and receive all 20 acknowledgements without timing out, what does it mean? Does it mean congestion or no congestion? It means no congestion. Should we increase or decrease CW? We should increase. However, since we are at the threshold already, we increase by adding 1 maximum segment, equivalently adding 1 kilobyte. So the 20 becomes 21, 22, 23, 24, and 25 kilobytes, assuming that at these transmissions here, from 19 to transmission 24, we did not have any timeout, so we were always increasing by adding the equivalent in bytes of 1 maximum segment, so 20, 21, 22, 23, 24, and 25. The example is finished, but I have 2 comments, and please focus with me. 2 comments. What happens if we get a timeout here? So at transmission 24, CW was 21, 2, 3, 4, 5. It was 25 kilobytes. If we get a timeout, which means I'm sending my 25 segments, but I'm not receiving all 25 acknowledgements in time, I get some timeouts. In that case, what happens to the next congestion window? It goes down all the way to 1, right? It goes down all the way to 1 maximum segment, or equivalently 1 kilobyte. What else happens? The threshold gets updated, and the new threshold becomes half of the congestion window. If this is 25, then the new threshold is only 12.5 kilobytes. 12.5 kilobytes, and the congestion window is equal to 1. So if we just follow the transmissions here, what will be the new congestion window values? 1, and then 2 because we double, and then 4 because we double, and then 8 because we double. If we're still fine with no timeouts, the 8 needs to be 16. However, we don't go to 16 because remember the threshold was 12.5, so the next congestion window is 12.5 kilobytes. And then if we're okay, no timeouts, 13.5, 14.5, and so on. So that's my first comment here. What happens if we get a timeout at that time? What happens are 2 very easy things. First of all, the next congestion window at time 25 becomes only 1 kilobyte, and secondly, the threshold becomes half of the congestion window. So if this is 25k here, if this is 25k, the next threshold becomes 12.5, and then we go again, exactly like this. So this is the first comment. Now, the second comment is here. I have at the very beginning, we mentioned that usually the threshold starts with 64 kilobytes. So the first value of the threshold is 64 kilobytes. But here you see a threshold of 32. So what could this possibly mean? I mean, one of the things that this could possibly mean is that what you see here is not the first transmission. So it is not the very first transmission over a TCP connection. No, before that we had transmissions, and since this is 1K, so we had a timeout before, right? We had a timeout before, so the transmission here at instance -1, let's say, before that transmission, the value of the congestion window was something higher. But we had a timeout, so the next one was 1 kilobyte, and this is where we started the example. So my question here, what could have been the congestion window before time 0? Again, there is only one way to answer this question. There is only one way. Since this congestion window is equal to 1, it means if we had something before, it must have been a timeout. We see the 1 if we have a timeout, right? So it must have been a timeout. Since we had a timeout, what was the value of the congestion window before? Remember also, at timeout, the threshold becomes half of the congestion window. So the only possibility here is that the previous congestion window was double of that threshold. So it was 64 kilobytes. So at time -1, or at the instant before time 0 here, at the index before 0, the congestion window was 64 kilobytes and we got a timeout. Let me think of the opposite way. Imagine it was 64, CW was 64, and we get a timeout. What would happen next? CW goes down to 1, which is what we see here, and also the threshold becomes half of the congestion window. Half of 64 is 32, which is precisely what you see, and then we continue exactly as in the example. So this finishes our discussion, and the example that I've explained here is also explained in text, and that's enough. This summarizes today's lecture, and next time I will see you with UDP, inshallah, User Datagram Protocol. Assalamu alaikum wa rahmatullah.